Alright, so in this video, I'm gonna be explaining another important article with the title Beyond GNNs, an efficient architecture for graph problems. This AAAI paper in 2022. Despite their popularity for graph structured data, existing graph neural networks have inherent limitations for fundamental graph problems such as shortest path, K connectivity, minimum spanning tree, and minimum cuts. So in these instances, it is known that one needs GNNs of high depth, scaling a polynomial rate with the number of nodes n, to provably encode the solution space in turn affecting their statistical efficiency. So they propose a new hybrid architecture to overcome this limitation that they call it GNN plus networks, involve a combination of multiple parallel low depth GNNs along with simple pooling layers involving low depth fully connected networks. And then we provably demonstrate that for many graph problems, the solution space can be encoded by GNN plus networks using depths that scales only polylogarithmically in the number of nodes. This also has statistical advantages that we demonstrate via generalization bounds for GNN plus networks. So the basic GNN plus block is like this. So n is the neighborhood of node I, this n, and the aggregation and combination is performed via simple one or two layer full connected networks, also known as multi-layer perceptrons. So our proposed GNN plus network consists of one or more layers of GNN plus block that is shown in figure 1. The GNN plus block comprises of R parallel GNN multi-layer perceptron networks followed by S parallel fully connected network modules for pooling, where R and S are hyperparameters of the architecture. More importantly, we restrict the R GNN MP modules to share the same set of weights. Hence, the parallel GNN MP modules only differ in the way the node embeddings are initialized. So we will focus on degree D graphs of maximum node degree D with n nodes and diameter D. We consider the fundamental graph problems of computing, for example, approximate all pairs shortest path in the undirected graphs. So they did some experiment, and you know the definition of effective resistance, and they define affinity for any two vertices. A is the probability that U and V is connected in G. And also another problem that they are trying to solve is clustering minimum cuts and spanning trees. So the spectral clustering of G corresponds to the cut obtained by taking the sign of eigenvector corresponding to the second smallest eigenvector. So the theorem says that there exist GNN plus networks for computing a global minimum cut and minimum spanning tree with n nodes and maximum degree D. I think this paper is from Google, and they are interested in numerical approximation of these shortest spanning tree and many min cut problem, the classical problems. So that's why by this architecture they are trying to solve it. For example, this is the network architecture for approximating all pairs shortest paths in the unweighted graph. So they are training this to saying that as a black box, input output. But you know the output, you know the distance between any two nodes, so you can learn it. So they're just learning what we want to do. For example, the shortest path, you can see it here, the shortest path distance. But the encoder is also important, so that's why they use this breadth first search of S1 and D, S2 and D. The BFS model is breadth first search. That in search algorithm for graphs, we have breadth first search and depth first search. From simple computer science, you know that. And for encoders, so they use this breadth first search between set of S1 and D. So the sets S1, S2, Sk, they are randomly chosen. They are randomly chosen subsets of the vertex set. So, and you have diameter D graphs. So for diameter D graphs, we can have this breadth first search as encoders of these random sets. So these are the inputs, and the outputs is what we know. We know that we already know the distance between any two nodes, so we can learn it. Same tricks for minimum cuts and other classical problems, like minimum spanning tree. And so they did for problem of minimum spanning tree, minimum cut, effective resistance. Calculation of this is very challenging, but these people in Google are trying to solve it by learning it. And then shortest paths.